Hello, students. Today we are going to talk about something really fundamental in semiconductor physics, the Fermi-Dirac distribution function and the Fermi level. I know the names might sound technical at first, but they actually answer a very intuitive question. In a solid, which energy states do electrons occupy and why? And once we understand that, we can explain why some materials conduct electricity so easily, why some don't conduct at all, and why semiconductors sit so beautifully in between and make modern electronics possible. Let's start with the idea of Fermi level. Imagine we freeze a material down to absolute zero, which is also known as 0 Kelvin. At that temperature, electrons don't have any thermal energy left to jump into higher energy states, so they fill up the lowest available states first. The Fermi level is simply the energy of the highest occupied state at 0 Kelvin. But why is this concept so important? Because even when the temperature isn't zero, the position of this Fermi level helps us estimate how likely it is for electrons to occupy different states, and that probability is what ultimately controls the electrical properties of the material. Now, what does this look like in conductors like copper or aluminium? At absolute zero, electrons fill up states up to the Fermi level, and in metals, this Fermi level actually lies inside a band of allowed energy states, which is the conduction band. That means even without extra energy, there are always empty states very close by in energy, so electrons can easily move under an applied voltage. This is why metals conduct so well. There are free electrons available, and the Fermi level sitting inside a partially filled band keeps those electrons mobile. Now let's look at semiconductors. At absolute zero, the valence band, which is the lower band, is completely filled, and the conduction band, which is the higher band, is completely empty. Between them lies the band gap. This is the energy range where electrons simply cannot exist. For an intrinsic or pure semiconductor, the Fermi level lies right in the middle of this band gap. Why? Because it reflects a balanced situation. Same chance of electrons jumping up to the conduction band as there is of holes appearing in the valence band when temperature increases. But at 0 Kelvin itself, no electrons have the thermal energy to cross the gap. So the semiconductor acts like an insulator. To aid this understanding, we have shown this picture for intrinsic semiconductor, N-type semiconductor, and P-type semiconductor. You can see that for intrinsic semiconductor, the Fermi level, which is denoted as EFI, lies right in the middle of valence band and conduction band. In N-type semiconductor, the Fermi level, which is denoted as EF, shifts up towards the conduction band, while in P-type semiconductor, the EF Fermi energy level shifts down just above the valence band. Why this happens, we are going to discuss this in the upcoming slides. You might wonder, why can't we just say below the Fermi level electrons, above no electrons? The reason is electrons are fermions, meaning they have half integer spin and they obey the Pauli exclusion principle. This rule says no two electrons can occupy the same quantum state at the same time. So instead of having all electrons pile into the lowest state, nature forces them to spread out, and the Fermi-Dirac distribution helps us calculate exactly how this spreading happens at any temperature. To see why this matters, compare with photons, which are bosons. Bosons can all pile into the same energy states. That's why we can have laser light where many photons are in the same mode. But electrons can't do that. They must fill separate energy states because of the Pauli exclusion principle. This difference between fermions and bosons is fundamental, and it is the reason why metals and semiconductors behave so differently from things like light. The Fermi-Dirac distribution function tells us the probability that an electron state at energy E is occupied at temperature T. The formula is Pe is equal to 1 upon 1 plus E raised to the power E minus EF upon kT, where Pe is the probability of an electron occupying the energy state E. EF is the Fermi energy, Boltzmann constant is denoted by K, and T is the absolute temperature. Now, what is the probability of a particle to occupy a certain level at T equal to 0 when electron's energy is greater than the EF, the Fermi level? So doing this simple calculation, as you can see on the screen, PE is denoted by 1 upon 1 plus e raised to the power e minus EF upon kT. When E is greater than EF, then E minus EF upon kT becomes infinity. Therefore, PE becomes 0. This means no electron have the energy above EF because there is no thermal energy to push them there. What happens when the energy of electron is lesser than EF? So again, in the formula of Fermi-Dirac distribution function, when E is less than EF, then E minus EF upon kT becomes minus infinity. This makes PE is equal to 1. This step-like behavior is what makes the Fermi level at 0 Kelvin so clear and so important, because this shows that all electrons occupy the energy states below the Fermi level at 0 Kelvin. This shows that all energy states below Fermi level are filled and those above the Fermi energy are completely vacant at 0 Kelvin. Again, what happens when E becomes equal to EF at T equal to 0 Kelvin? At the Fermi level itself, the probability is always 0.5. You can see that the formula for Fermi-Dirac distribution function becomes 1 upon 1 plus e raised to the power 0 when we put E equal to EF in the denominator of Fermi-Dirac distribution function. It makes PE is equal to half, which is 0.5. That means at any temperature, the Fermi level marks the energy where an electron has 50% chance of occupying the state. This is true even as the temperature changes. When temperature increases, the sharp step in the distribution function becomes smoother. Some electrons get enough thermal energy to jump to the states above EF, leaving holes behind below EF. This redistribution of electrons is why intrinsic semiconductors start conducting at higher temperatures. More electrons cross the band gap. In an intrinsic semiconductor, where no extra impurities are added, the Fermi level sits right in the middle of the band gap. That's because the number of electrons in the conduction band equals the number of holes in the valence band. So it's a balanced system statistically. And this can be easily understood with this small derivation. We know that Fermi-Dirac distribution function is PE is equal to 1 upon 1 plus e raised to the power e minus EF upon kT. Now let's say that the number of electrons in conduction band, which is denoted by Nc, is n upon 1 plus e raised to the power Ec minus EF upon kT. And similarly, number of electrons in valence band can be described as n equal to 1 upon e raised to the power EV minus EF upon kT, where n is the total number of electrons, which is Nc plus Nv. So when we are going to put these two expressions in the formula n equal to Nc plus Nv, we are going to get n equal to n upon 1 plus e raised to the power Ec minus EF upon kT plus n upon 1 plus e raised to the power EV minus EF upon kT. Now when we solve this equation, we are going to get this particular equation, which is e raised to the power EC plus EV minus 2EF upon kT equal to 1. This makes it EC plus EV minus 2EF upon kT equal to 0. So therefore we have EC plus EV minus 2EF equal to 0, and therefore we have EF equal to EC plus EV upon 2. So this proves that the number of electrons in the conduction band equals the number of holes in the valence band. So it's a balanced system statistically. Now let's see what happens when we dope the semiconductor to make it n-type by adding donor atoms. These donor atoms add energy levels just below the conduction band, so electrons can easily jump into the conduction band. As a result, the probability of having electrons near the conduction band increases and the Fermi level shifts upwards closer to the conduction band edge. In p-type semiconductors, we add acceptor atoms which create empty energy levels just above the valence band. Electrons from the valence band can jump into these acceptor levels, creating holes. Now, the probability of occupancy near the valence band becomes higher and the Fermi level moves closer to the valence band edge. So, we can summarize the entire discussion on Fermi-Dirac distribution and Fermi level into few points, such as the Fermi level distribution function explains how electrons fill up energy levels, taking the Pauli exclusion principle into account. The Fermi level marks the dividing energy at 0 Kelvin and shows us where the probability of occupation is zero 0.5 at any temperature. The place where Fermi level lies inside a conduction band in the middle of the band gap or closer to conduction or valence band edges tells us whether a material behaves as a conductor, an insulator, or a semiconductor. These ideas explain why adding a few atoms of dopant can change the entire electrical behavior of a material, and that's what makes semiconductor physically so powerful and fascinating. Thank you all.